The bottom line, I simply want to make ever better car, no matter what kind of the powertrain they have.
Something bold just shook the foundation of the car industry, and it didn't come from a battery. While most automakers are sprinting toward electric, Toyota has unveiled a breakthrough that takes a very different route. It's a familiar concept, but with a powerful twist that could redefine what clean mobility looks like. This isn't just another innovation. It's a move that could shift the balance of the entire industry. Is this the beginning of a new energy era, or a direct challenge to the EV throne? The game changer. Toyota's bold new direction in hydrogen-powered engine technology is setting the stage for a seismic shift in the global automotive industry. While electric vehicles, EVs, have dominated headlines and market strategies in recent years, Toyota's latest innovations suggest a parallel and potentially superior path forward. The company's president and CEO, Koji Sato, has made it clear that Toyota is doubling down on hydrogen as a long-term solution to sustainable mobility, highlighting the limitations of battery electric vehicles in terms of raw materials, charging infrastructure, and performance scalability. Sato claims this new hydrogen engine design could destroy the entire EV industry by offering cleaner energy without the logistical and environmental trade-offs that EVs currently face. Unlike traditional internal combustion engines or even battery electric drivetrains, Toyota's hydrogen-powered technology is built around fuel cell electric systems, which produce electricity by combining hydrogen with oxygen, emitting only water as a byproduct. This process, already commercialized in vehicles like the Toyota Mirai, represents a zero-emissions alternative that retains many advantages of gasoline engines, such as quick refueling and long driving range. Toyota's hydrogen cars can be refueled in about 5 minutes, significantly faster than the charging times of most EVs, and achieve ranges comparable to, or even exceeding, those of battery electric counterparts. This new set of hydrogen technology differentiates itself by addressing multiple sectors outside consumer automobiles. Toyota is investing in hydrogen for buses, trucks, industrial equipment, and even maritime purposes, forming an entire ecosystem surrounding the technology. Equipment like the Toyota Sora bus and hydrogen semi-truck prototypes shows that hydrogen is not merely a niche experiment. It is being built for real-world application. The Japanese automaker's move is a direct response to the practical limitations of lithium-ion batteries in heavy-duty and long-range scenarios, with hydrogen being framed as a more versatile energy solution. That latest revelation mirrors, in fact, the long-standing internal contrarianism of Toyota in the worldwide race to decarbonize every mode of transport. Other car manufacturers were bent on rushing into battery EVs. Toyota opted for a broader electrification strategy, including hybrids, plug-in hybrids, and fuel cells. Now, that approach pays off. It is from growing concerns regarding sustainability issues such as rare earth mining, battery disposal, and strain on power grids that one can see the hydrogen vision of Toyota as an attractive, clean alternative with lesser dependence on scarce materials. If successful, this technology could reshape the dynamics of the industry dramatically, taking on the current dominance of battery EVs and reinterpreting the future of clean mobility. But what exactly makes this clean energy breakthrough so different under the hood? How hydrogen fuel cells work. Hydrogen fuel cell technology operates on a clean and efficient electrochemical process that converts hydrogen gas into electricity. In Toyota's fuel cell electric vehicles, like the Mirai, hydrogen is stored in high-pressure tanks and fed into a fuel cell stack, where it reacts with oxygen from the air. This process occurs without combustion. Instead, a catalyst facilitates a reaction that splits hydrogen molecules into protons and electrons. The electrons flow through an external circuit, generating electric power that drives the vehicle's electric motor. The only byproduct of this energy conversion process is pure water vapor, making hydrogen fuel cells a zero-emission technology at the point of use. Unlike internal combustion engines that release carbon dioxide, nitrogen oxides, and particulates, hydrogen-powered vehicles emit nothing but water from the tailpipe. This positions fuel cells as one of the cleanest propulsion systems available today, provided that the hydrogen itself is sourced sustainably, for example, from electrolysis, powered by renewable energy rather than fossil fuels. The hydrogen fuel cell mechanism of Toyota is a major breakthrough, combining environmental advantages with performance that many a gasoline vehicle can boast about. The fuel cell stack generates enough electricity to power the car's electric motor, then and there, just like any other gaseous fuel-burning vehicle, without the need for heavy batteries. On the other hand, it may have a ribbon-thin weight-saving design, speedy acceleration, and performance that can stay high when under a load. The refueling was a matter of minutes, usually less than 5, and was completed cold with a full tank, giving a driving range of about 650 kilometers. That is over 400 miles, depending on car model and driving conditions. Safety and efficiency form the hallmark of Toyota's fuel cell technology. Hydrogen tanks are developed in carbon fiber blended material construction, tested against extreme conditions, and equipped with sensors to detect minimal leaks. Furthermore, to ensure durability and high output, the fuel cell stack is designed and has enjoyed a lengthy period of real-world testing since the prototype Mirai was introduced to the market in 2014. Advanced engineering by Toyota is leading and supporting the momentum gained by hydrogen fuel cells in other markets, such as heavy transportation and industrial energy, towards the establishment of a wide hydrogen economy. Performance benefits. Toyota's hydrogen fuel cell vehicle, FCEVs, offer a compelling blend of performance benefits that rival and even exceed those of battery electric vehicles, BEVs, and traditional combustion engines in key areas. One standout feature is instant torque delivery, made possible by the electric motor powered by the fuel cell stack. Like battery EVs, hydrogen vehicles provide rapid acceleration from a standstill, but without the performance degradation associated with heavy battery packs or prolonged high-load driving. This makes FCEVs ideal for urban and highway use, as well as for heavier vehicle categories like trucks and buses. Driving range is another major advantage of Toyota's hydrogen-powered models. The latest generation of the Toyota Mirai boasts a real-world range of approximately 650 kilometers over 400 miles on a full hydrogen tank. This range significantly outpaces most current battery electric vehicles, especially under cold or high-speed conditions where EV efficiency drops. Moreover, hydrogen's high energy density by weight allows for extended driving distances without the need for large, heavy batteries, making it more suitable for long-haul transport and fleet operations. Refueling speed is one of the game-changing components of hydrogen technology from Toyota. Hydrogen vehicles are refueled in about 3 to 5 minutes for a tank capacity comparable to a gasoline car. However, EVs can take 30 minutes to hours, depending on the charger type. It thus eases range anxiety and ensures a seamless user experience, especially in commercial applications where downtime needs to be minimized. Toyota has shown consistent refueling performance across personal vehicles and commercial prototypes alike, which reveals the scalability of its solution. Furthermore, the company has placed great emphasis on the provision of uniform operation, irrespective of any load or type of terrain. The performance level of power delivery is made stable even under very strenuous driving conditions through the provision of real-time power generation from the fuel cell stack. Hydrogen FCEVs hold their output over the full tank cycle, unlike BEVs, whose performance diminishes as the battery charge runs down. The regeneration use of deceleration energy by Toyota has added to the energy efficiency factor of the overall system. The combination of fast refueling, very long driving range, and smooth torque precisely suits those vehicles to endure different driving conditions and demands. Safety and durability of hydrogen tanks. Toyota has prioritized safety and durability as core pillars in the development of its hydrogen fuel cell vehicles, particularly in the design of its hydrogen storage tanks. These tanks are constructed using advanced carbon fiber reinforced polymer materials that are lightweight yet incredibly strong. Each tank is engineered to withstand pressures up to 70 megapascals, far exceeding the operating pressures required for fuel cell functionality. This high level of structural integrity ensures that the hydrogen is stored securely, even under extreme conditions such as high-speed impacts or rollover accidents. To ensure the tanks meet the highest safety standards, Toyota subjects them to rigorous testing protocols that simulate real-world and extreme events. These include fire exposure, ballistic tests, drop impacts, and crash simulations. In these evaluations, hydrogen tanks must maintain their structural integrity without rupturing or leaking. Toyota's hydrogen tanks have even demonstrated resistance to bullets in controlled testing environments, an impressive benchmark that underscores the robustness of the design. These tests align with international safety certifications and exceed typical automotive safety requirements. Hydrogen systems of Toyotas have advanced safety monitor technology, which complements their rugged engineering. The fuel systems contain hydrogen leak detectors, automatic shut-off valves, and pressure relief devices that will activate during exceedingly rare instances of a system fault. In case a leak is detected, the vehicle seals the tank and safely vents hydrogen into the atmosphere, where low molecular weight allows for quick dispersion. This redundancy greatly reduces any possibility of fire or explosion. Thus, hydrogen fuel cell vehicles will be comparably safe, if not actually safer, than their gasoline or battery electric counterparts. Endurance is one of the high points of durability among the heavy-duty Toyota hydrogen storage systems. The tanks are designed to last the whole life of the vehicle, typically 10 to 15 years, without such replacements. Unlike lithium-ion batteries, which degrade on account of charge cycles and temperature exposure, hydrogen tanks maintain performance and pressure integrity throughout their life. This durability reduces maintenance costs and improves the commercial fleet and high-use applications for fuel cell vehicles. After more than 10 years of real-world performance experience in vehicles such as the first and second generation of Toyota Mirai, the technology has proven both safe and reliable for everyday use. Environmental footprint. Toyota's hydrogen fuel cell vehicles are designed to minimize environmental impact across their entire operational life, offering a zero-emission alternative to traditional combustion engines and even many electric vehicles. At the core of this environmental advantage is the fuel cell system itself, which generates electricity by combining hydrogen with oxygen from the air. The only byproduct of this electrochemical reaction is water vapor. No carbon dioxide, nitrogen oxides, or particulate matter are emitted during vehicle operation. This makes hydrogen-powered vehicles among the cleanest forms of transportation available today when measured at the tailpipe. A key differentiator of Toyota's hydrogen technology lies in its potential for carbon neutrality, depending on how the hydrogen is sourced. Currently, most hydrogen is produced through natural gas reforming, grey hydrogen, which emits carbon dioxide during production, produced via electrolysis using renewable energy sources like solar or wind. When vehicles use green hydrogen, the entire energy cycle, from production to end use, can be carbon-free, offering a truly sustainable mobility solution far beyond what's currently feasible with fossil fuel vehicles or even some grid-powered EVs. Also, hydrogen fuel cell vehicles can avoid most of the environmental problems associated with producing and disposing of batteries. Unlike battery electric vehicles, BEVs, which need vast quantities of rare earth minerals such as lithium, cobalt, and nickel, these metals are often mined under environmentally damaging and ethically questionable conditions. Instead, hydrogen systems by Toyota depend largely on materials always available. Hydrogen fuel cells also do not suffer the same degradation problems as lithium-ion batteries, which would reduce replacements and recycling problems associated with them. The preparedness of the environment, touching beyond the vehicles themselves, includes large commitments toward building hydrogen infrastructure and ecosystems. The company is investing in hydrogen production facilities and refueling stations, as well as cross-sector partnerships across transportation, energy, and industry. Such a holistic perspective bolsters its view to realize carbon neutrality by 2050 throughout its operations. As the world intensifies pressure to move away from fossil fuels, Toyota sees its hydrogen fuel cell technology as a large-scale answer that is clean and can withstand giving potency to these concerns of domestic air quality and global climate change. Toyota's strategy, which measures a product's overall environmental cost from production to disposal, also fits with the growing cultural shift toward life cycle sustainability. The European Commission started creating rules for well-to-wheel emissions reporting in 2023, which might give preference to green hydrogen-powered vehicles over electric vehicles that are charged by fossil fuel grids. Toyota's focus on clean production and long-term efficiency gives hydrogen technology a strong advantage in the larger sustainability discussion as consumer awareness of the hidden environmental costs of electric batteries grows. Toyota didn't stop at the blueprint, they built something to prove it. Toyota Mirai. The Toyota Mirai stands as a pioneering example and proof of concept for hydrogen fuel cell vehicle (FCEV) technology in the real world. First introduced in 2014, the Mirai became one of the world's first commercially available hydrogen-powered vehicles, showcasing Toyota's long-term commitment to sustainable transportation beyond battery electric solutions. Now, in its second generation, the Mirai has undergone significant improvements in performance, range, efficiency, and design, serving as a live demonstration of the viability of hydrogen as a mainstream automotive fuel. The second-generation Mirai, launched in 2020, features a completely redesigned fuel cell system, a more aerodynamic and premium rear-wheel drive platform, and a longer driving range. With an estimated range of up to 650 kilometers, over 400 miles, on a full hydrogen tank, it outperforms many battery electric vehicles, BEVs, in terms of distance per refuel. It also benefits from fast refueling times, typically under 5 minutes, delivering a user experience much closer to that of traditional gasoline cars. These features make the Mirai not just a concept, but a fully functional and practical daily use vehicle. Toyota has developed the Mirai as an experimental platform to monitor and refine every parameter defining its hydrogen system, from fuel stack efficiency to tank security to drive performance. The car is equipped with high-pressure carbon fiber hydrogen tanks, a next-generation fuel cell stack with high power density, and regenerative braking systems for improved energy efficiency. With thousands driving on the road globally, in hydrogen-forward markets in Japan, California, and parts of Europe, the Mirai has provided some invaluable real-time data for the next step in hydrogen mobility projects. Mirai is much more than just a consumer transportation vehicle. Thanks to its success, Toyota is able to use hydrogen fuel cell technology in other mobility sectors. Development and deployment information from Mirai directly influenced projects such as the hydrogen bus Toyota Sora, heavy-duty fuel cell trucks, and even stationary power systems. The Mirai has validated Toyota's hydrogen strategy by proving its concept that hydrogen vehicles can be reliable, efficient, and user-friendly. It laid down certain foundations of the larger hydrogen ecosystem the company is now developing for the future of zero-emission mobility. The Mirai aspires to an achievement more symbolic than of an engineering nature, as judged by public perception and government policy discourse on hydrogen. Among the many ways that the Mirai was brought up in Japan was during the Tokyo 2020 Olympics, where it was among the few electric vehicles used to ferry the athletes and officials around, as part of a display of innovations in sustainability tagged Tokyo 2020. This raised hydrogen visibility as not only a clean technology, but also a national asset. Japan's Ministry of Economy, Trade, and Industry referred to the Mirai as a turning point in positioning hydrogen as a pillar of Japan's future energy policy. In consequence, the advanced world would be following suit on the Mirai as a case study to model their hydrogen mobility framework. Aside from the technical validation, that is another vehicle significance, that of culture and diplomacy. In addition, beyond cars, Toyota's hydrogen fuel cell technology is designed not just for personal vehicles, but for scalable applications across multiple transportation and energy sectors. The company views hydrogen as a cornerstone of a broader clean energy ecosystem, and its fuel cell systems have already been adapted for use in buses, commercial trucks, trains, ships, and stationary power generation. This expansion demonstrates that hydrogen can meet the diverse energy needs of both mobile and fixed systems, especially in applications where battery electric solutions face limitations due to weight, charging time, or infrastructure constraints. One of the most prominent examples of scalability is the Toyota Sora, a hydrogen fuel cell bus introduced for public transit in Japan. These buses use the same core fuel cell system as the Mirai, but are scaled to meet the demands of large, heavy-duty vehicles. The Sora has been deployed in Tokyo and other major cities, especially in preparation for high-profile events like the 2020 Olympic Games. With zero tailpipe emissions, fast refueling times, and quiet operation, the Sora bus proves that hydrogen can efficiently power large urban transportation networks. Also, to develop hydrogen-powered heavy trucks for long-distance freight, Toyota is working with commercial and logistics companies. One endeavor in this partnership is to modularize the Mirai fuel cell system into a form that can be used on trucks operating in ports and along highways. These trucks use hydrogen due to its high energy density and fast refueling capability, allowing for almost no downtime and operational efficiency. Toyota has crossed hydrogen maritime applications, including Chase Zero, a hydrogen-powered catamaran launched in New Zealand, proving that hydrogen is employable in a wide range of applications for water transport. Apart from mobility, Toyota is looking into hydrogen as a clean energy option for off-grid and backup power generation. Stationary fuel cell systems can supply power to buildings and disaster relief efforts, as well as industrial facilities. They emit only water and heat and can be used in remote areas that lack reliable grid access. Another exhibit of Toyota's commitment to scalability is in its involvement in hydrogen infrastructure build-out, cooperating with governments and private companies to expand hydrogen production, transportation, and refueling networks. Such an all-encompassing view presents Toyota's hydrogen technology not only as an automobile innovation, but essentially as a future energy solution. Particularly noteworthy is the way in which Toyota's hydrogen aspirations complement the expanding global movement toward decentralization of energy systems, particularly in the wake of geopolitical energy crises and climate-driven disasters. Hydrogen microgrids, driven by stationary fuel cells, provide a robust substitute for centralized grids in regions such as Australia and parts of Africa where they are weak or undeveloped. Following the 2011 Fukushima accident, Toyota's H2-powered backup systems were even tested in Japan, highlighting their significance in national energy security plans. Hydrogen enables energy to be produced where it is consumed. As Professor Katsuhiko Hirose, a key architect of Toyota's fuel cell program, once said, "This local generation and usage principle is gaining traction with governments and non-governmental organizations seeking to achieve both sustainability and energy access autonomy." Infrastructure development. For Toyota's hydrogen vision to scale successfully, infrastructure development is just as critical as the technology itself. Hydrogen-powered vehicles, unlike gasoline or battery electric cars, require a network of high-pressure refueling stations specifically designed to handle, store, and dispense compressed hydrogen gas. Recognizing this, Toyota has been actively involved in supporting the expansion of hydrogen infrastructure, working closely with governments, energy providers, and industry partners to establish reliable and accessible hydrogen refueling networks, particularly in key markets like Japan, the US, and parts of Europe. Japan has been one of the most aggressive countries in building hydrogen infrastructure, partly due to Toyota's leadership and lobbying efforts. The Japanese government, in collaboration with automotive and energy companies, launched the Hydrogen Highway Initiative creating a growing network of hydrogen stations linking major cities. Toyota's home market now supports a national rollout strategy for FCEVs, with nearly 200 operational stations and plans for continued expansion, aligning with the country's broader goal of becoming a hydrogen society by mid-century. In California, the state with the most advanced adoption of hydrogen vehicles in the US, Toyota has played a significant role in the installation of hydrogen stations. More than 50 hydrogen stations have been built throughout the state, with more in the works, thanks to collaborations with businesses like First Element Fuel and Shell, and support from state organizations like the California Energy Commission. Toyota has provided both technical and financial support, guaranteeing that stations adhere to safety and performance requirements that align with its own fuel cell technology. In its outlook, Toyota believes that hydrogen infrastructure will expand from the urban center to serve various industries and transport modes. The company favors a multi-sector approach to hydrogen that includes passenger vehicles, buses, trucks, trains, ships, and even stationary power generators. This would be on account of drawing from the same hydrogen supply chain, therefore optimally improving the infrastructure economics with shared use and high volume demand. By developing a holistic and systemic refueling network, Toyota plans to abolish the chicken and egg dilemma that has previously hindered acceptance of hydrogen and to fast-track the world towards cleaner energy solutions at scale. An emerging factor supporting the hydrogen infrastructure growth is the growing interest in specific non-automotive applications. These eventualities may become unexpected allies in scaling up adoption. For example, some major airports and logistics hubs, Tokyo's Haneda Airport and Germany's Hamburg Airport, to name just a few, look into hydrogen-powered ground support equipment, which will use the same fueling technology as Toyota's vehicles. By 2030, according to the International Energy Agency, IEA, global industrial hydrogen demand related to steel production, shipping, and backup power is expected to triple, thereby providing new economic arguments for developing hydrogen refueling networks. Hydrogen is not just about cars, it's about forging a new energy culture, said Toyota President Koji Sato in a recent interview. This broader use case could be decisive in making hydrogen stations more common and profitable, thereby propagating the effects of public sector decarbonization mandates. Challenges ahead. High production and vehicle costs remain a critical barrier to hydrogen adoption. Fuel cell systems rely on expensive materials, particularly platinum catalysts, and current hydrogen production methods are costly. Today, grey hydrogen from natural gas costs around $1 to $2.50 per kilogram, while green hydrogen sits at $350 to $600 per kilogram, making it significantly more expensive than conventional fuels. Toyota's own Gen 3 fuel cell stack shows a 20% efficiency improvement, but mass adoption still hinges on reducing manufacturing and catalyst costs to compete with diesel, gasoline, and BEVs. Lack of widespread refueling infrastructure poses another major challenge. There are only a few hundred hydrogen filling stations globally, mostly concentrated in Japan, California, and parts of Europe. In the US, almost all 53 public stations are in California, and several have shut down due to reliability issues or lack of customers. Toyota faces criticism and even lawsuits from Mirai owners over station closures and fuel access limitations in California. Solutions like Europe's twin mid-flow dispensers are promising, but scaling station networks globally requires massive investments and alignment with competitors and governments. In the production of hydrogen, energy inefficiencies and environmental trade-offs are still substantial. Energy-intensive processes like electrolysis and reforming are used to produce hydrogen, and even green hydrogen pathways can lose 50 to 70% of their efficiency as a result of compression, transport, and reconversion. Furthermore, strict leakage controls and sourcing from renewable sources are crucial because leaked hydrogen has strong greenhouse gas impacts that are up to 11.6 times stronger than carbon dioxide. These energy-related issues highlight why battery electric cars continue to have a distinct energy efficiency advantage. In the end, hydrogen must struggle to find its niche against a fast-moving EV world, particularly in the area of passenger automobiles, while under political and market pressure. Battery technologies used for BEVs are much cheaper than those for hydrogen. In addition, mature charging infrastructure for BEVs is developing fast acceptance among the public. Hydrogen vehicle sales worldwide in 2024 barely amounted to above 1,700 units, against those of over 380,000 for BEVs in the US. For instance, US tax credits for green hydrogen, the 45V credit, are in danger of being restructured, and billions of dollars worth of new green projects have been delayed. According to Toyota, the future of hydrogen very much depends on tech advancements as well as government-friendly regulations and infrastructure partnerships. Yet, even with these roadblocks, the real disruption may have only just begun. The battle begins. Toyota's announcement of its hydrogen combustion engine, NEAT, expected by late 2026, has injected a provocative challenge into the EV-dominated market. Unlike fuel cell systems that convert hydrogen into electricity, this new engine combusts hydrogen directly within a modified internal combustion engine architecture, producing only water vapor emissions. This strikes at the heart of the traditional battery electric BEV advantage. Despite current EV dominance, hydrogen evades many EV limitations, such as lengthy recharge times and dependence on rare earth materials. Toyota's CEO Koji Sato went so far as to claim the engine could destroy the entire EV industry, a statement that signals Toyota's intention to recalibrate the competitive landscape. Toyota's new hydrogen engine highlights a major blind spot in BEV scalability, charging speed, and resource dependency. BEVs rely heavily on lithium-ion batteries, components that involve resource-intensive mining and invasive supply chains, raising ecological and geopolitical concerns. In contrast, hydrogen engines offer near-instant refueling in 3–5 minutes and substantial driving ranges comparable to gasoline vehicles, without pressing demands on battery raw materials. If mass-produced, Toyota's design could elevate user expectations for charging convenience, pushing mainstream EVs to innovate faster or integrate hybrid hydrogen systems. In response, the larger industry is already portraying hydrogen as an additive to BEVs rather than a rival. Toyota itself highlights a multi-pathway strategy, implementing various technologies: hydrogen, plug-in, battery, and hybrid, where appropriate, and all geared toward decarbonization. A trend toward hybrid ecosystems is indicated by cooperative projects like Toyota and BMW's joint hydrogen fuel cell venture. For heavy-duty transportation, long-distance logistics, and other uses where BEVs have trouble with weight or recharging logistics, automakers believe fuel cells may be a better option. Considerable claims notwithstanding, the sector is still grappling with challenges such as the resilience of the electric vehicle market, in addition to its infrastructure. BEVs presently realize an average of around 80% energy efficiency, as opposed to around 40% for hydrogen-based automobiles, and possess a much more mature and widespread global charging network. In the mainstream passenger market, the sugar of choice remains BEVs, indeed bulging ahead of hydrogen. Thus, there are about 40 million BEVs sold in 2024 and only about 14,000 hydrogen units sold fully around the globe. Consequently, new investments in hydrogen hubs and regulatory frameworks will probably draw the recalculation, albeit with issue-making pressure on the automakers and policymakers to revisit energy pathways, rather than immediately dethroning BEVs' hegemony. Perhaps one of the strongest signals of hydrogen's increasing importance has come from Motorsports, a testbed, if not the vital test ground, for next-generation automotive technologies in extreme conditions. One of the latest competitions, Kamikaze in from Toyota, has been made in the Super Taikyu Endurance Series in Japan, not a fuel cell vehicle, but a fundamental hydrogen-burning engine. "We are not giving up on internal combustion," said Akio Toyoda, chairman of Toyota and former CEO, during a race event. "We want to keep options open. It is really contention proof of concept about how hydrogen combustion can perform reliability stretch, thereby generating interest from those said to endorse high-appetite cars and from industry insiders who view the electric drivetrain as lacking much of the emotional and mechanical feedback associated with traditional engines." Thanks for watching. If you found this as exciting as we did, don't forget to like the video, subscribe for more future-shaping tech updates, and drop a comment. What do you think about Toyota's hydrogen breakthrough? Curious for more? Click the next video on your screen to keep exploring the future of mobility. See you there.